Let us enjoy science by looking into it with slightly more details. Explore and learn. I am Anil Kumar. In this video, we are going to explore some concepts about science. The idea of taking a few topics in science is mainly to make our students understand how beautiful this subject is and how can we explore further to get more out of what is given to us. Now, in this video, we'll discuss a very important topic, and that is comparing size of atoms and ions. I'm taking a particular example where we're talking about sodium atoms and chlorine atoms. Now, sodium and chlorine can combine very easily to form NaCl, the common salt. Common salt, as you know, is one what we eat, right? It's a chemical substance, very useful for us in many different ways. Now, the question here is why sodium atoms are bigger than chlorine atoms. So, when we talk about elements, we are talking about these atoms. And then, are sodium ions bigger than the chloride ions? That is, when we talk about a molecule, for example, sodium chloride molecule, in that we could have sodium ions and the chloride ions. Sodium ion is the cation, positively charged, since one electron from the outermost orbit of sodium goes to chlorine, and that stabilizes and forms a very strong bond, NaCl, where effectively, since sodium atom has lost a valence electron, which is gained by chlorine, sodium attains a positive charge. So we call this cations, right? And anions with negative charge. Now the question is that why sodium atoms are bigger than chlorine atoms. And once they form a molecule, sodium chloride, as we just discussed, the second question is are sodium ions also bigger than chloride ions? That is what we need to figure out. Let us explore further with the help of their position in the periodic table. Now, size of atoms, how do we find relative size of atoms? Well, position of our elements in the periodic table do give us an idea about the size of atoms. So, if you look into the periodic table, let me write down the elements which are in period 3, right? So let me write period 3. In period 3, we have sodium and chlorine, both these elements, right? So it goes like sodium, right? Then we have magnesium, Mg, and we have aluminum, silicon, phosphorus, sulfur, and then we have chlorine and the noble gas argon. So you see there are 8 elements in period 3. 1, 2, 3, 4, 5, 6, 7, 8. Now, as we move from left to right, what happens to the size? Well, as we move from left to right, the size of these atoms decreases. You know, kind of like this. Can you tell me the reason why this is happening. So I'm giving you a visual look here. Well, that's just an visual look, right? Approximately. The size decreases. I'm trying to show you more bigger for sodium and smaller for chlorine or thereafter, right? So in a period, it decreases. The reason is very simple. As we move along in this period, the atomic number is increasing by 1. That means the number of protons and number of electrons are each increasing by 1. So there is definitely a higher force of attraction between the nucleus and the outer orbit. So it kind of comes closer and closer as we move to the right of a period, which results into decrease in the size of the atoms. Does make sense? So what I'm trying to say here, let's look at it once again. So what I did here is kind of gave you more insight of the atoms of sodium and chlorine. So, as I was saying, sodium and chlorine are between the inert noble gases, neon and argons, right? That's kind of important. Noble gases have filled in valence electron shells, making them monoatomic gases. So, this is an additional statement which we which is important, however, not so important for this particular video. Now, in between, I've given you starting with sodium, ending with argon, chlorine just before argon. So these are period 3 elements for us. Sodium has an atomic number of 11. That means there are 11 electrons and 11 protons. While in the nucleus, we have neutrons also. In case of sodium, we have 12 neutrons. So if I try to arrange them with a very simple model, so for sodium, I can write down that, well, let's have a nucleus here. And around the nucleus, we have the cloud of electrons, right? So somewhere in this space, we have electrons. So we'll put, for simplicity, the orbitals. The first one, we are putting two of them here, right? Kind of like this. And so that is, I'm writing here 1s2. So the first. Now, second one, after this, we have 8 there, right? So let's say, so these are the 8 ones, right? So let's put 4, then we have 5, 6, 7, 8. So that 8 takes care of 10 of the electrons. That is the structure of neon. Do you see that? So neon has this kind of a structure. Now we have the valence outer orbital in which there is one valence electron for sodium, and you can see it is kind of like this, right? Now what happens for chlorine? Let's go for chlorine now. So in case of chlorine, what we expect is something like this. So once again, we have a positive charge in the center where we have protons and neutrons, and in this case, we have 17 protons and 17 neutrons in the nucleus. Now we have to fit in 17 electrons, which will again go into these three, right? Okay, so let me just make the first s orbital where there will be 2, right? As it can take maximum of 2. So that takes care of 1s2. And then the next one will take 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So that takes care up to this part. And this is like a stable structure of neon. You write, sometimes we write neon this much, correct? Now we have the third shell. So let me just make this third, n equals to 3, right? Okay. Now here we have 7 electrons to be placed. So let me put the 7 electrons, correct? So 1, 2, 3, 4, 5, 6, and 1, 7. So we get our chlorine structure. Now, chlorine happens to be smaller than sodium mainly because here we have more electrons and protons, so higher attraction in chlorine. Is that okay? So that means this is smaller, right? So that gives smaller. Is that clear to you, right? Same number of orbitals, kind of, right? So, so these distances which we're talking about are very, very small distances. Let me give you an idea of the distance of this atomic radius, right? So when it is sodium, the atomic radius is almost 180 picometers. When it is chlorine, it is around 100 picometers. So you can see that the atoms of sodium are larger than that of chlorine. The reason being that there are more number of electrons and protons in chlorine with the third shell, right? So therefore the force of attraction is more and it's more compact, right? So this is more compact and therefore results into a smaller size. So I hope this part is clear how as we move from one element to another horizontally along a period, size decreases. So you can see size decreases, right? As we move right in a period. Perfect. So this is common in the whole periodic table, right? You can apply the same logic. Perfect. So that is how, when we learn a concept, we can always extend it. So we have approximate idea also that that is how it looks. And in sodium, there is only one electron in the outermost orbit, which we call the valence electron. And since there are only 11 protons and 11 neutrons as compared to 17 in chlorine, the force of attraction for sodium is less. So it can lose that outermost electron easily. In case of chlorine, it has a very high force of attraction because of these 17 protons trying to attract them inside. And more than that, every atom wants to become stable. Only then we can have a molecule. Perfect. So now let's go to the second part of it, which is looking into the ions. So now for ions, what I'm going to do here is make a simpler diagram. So simpler diagram means we have sodium here, right? Let me draw sodium. And what we notice is that sodium had an electron, the valence electron, in the outermost orbit, correct? And then we had chlorine, which had seven, right? Chlorine had seven. So one, two, three, four, five, six, seven. Now, what happens is that when we are trying to make a compound out of it, then the molecules being formed will result because sodium is going to release this and chlorine is going to attract it. Since this force of attraction is very high for chlorine, as you've seen, 17 protons in the nucleus are trying to pull these electrons. So it pulls this sodium, and what results is a sodium with one less electron, means positive charge, chlorine with an additional electron, negative charge. Since sodium has lost this particular outer 3s1 electron, this has vanished now. In the case of iron, right, it becomes smaller. You get the idea. it has lost the outermost valence electron, size decreases. So it decreases from almost 180 parts picometers to 116 picometers. So the ion which has lost one electron is now positively charged. It's called cation. Its radius is 116 pm. As far as the chlorine is concerned, it gained an electron. So this anion, which is now negatively charged, chloride ion, is much bigger and size becomes 167 picometers. You understand? So, because of that gain of electrons, now what really happens is in the outermost orbit of chlorine, there are 8 electrons. Now, these 8 electrons have force of expulsion. They expand thereby, right? So, too many, right? 8, right? So, they kind of expand and the size increases. You get the whole idea? And therefore, we can say that in case of sodium chloride, what has happened is that the sodium ions are not bigger, right? They are smaller than the chloride ions. Make sense? So the atom of sodium is bigger than that of chlorine. However, the ion of sodium is much smaller than that of chloride ions, right? So this statement is false. The first statement is true. Does make sense? Now, this concept can be applied to all other ionic compounds also. So, in the formation of an ionic molecule, what really happens is that those which release the electron, their size decreases, and those who gain electron, their size increases. So, cations are smaller in size than their respective atom size. And anions, the negatively charged particles, will be bigger than their atomic size. Makes sense? Correct? So, that is the, in short, the reasons about this. You can extend this and look into more ionic molecules, right? Where this logic can be applied. Perfect. I hope that helps. Feel free to write your comment, share your views. We are here to explore further and enjoy this journey of learning of science. Thank you and all the best.